Welcome to part 2 of our lesson on volume by cylindrical shells. I have on here about when to, thoughts to keep in mind when it comes to using the disk/washer method or the cylindrical shells method. Basically, it just amounts to which one's easiest to compute, right? Is it easiest to compute top and bottom boundary curves in the form of y is equal to f of x, or by left and right boundaries of the form x is equal to g of y? Which one's easiest to work with? Draw a separate sample rectangle of the region corresponding to a cross section of the solid. If you imagine the rectangle revolving around whatever point, it becomes a disk, washer, or a shell. So with that being said, here's an example. This graph shows the region in the first quadrant bounded by the curves y is equal to x squared and y is equal to 2x. A solid is formed by rotating the region around the line x is equal to -1. We first want to find the volume of this solid, this one up here. You can see that particular kind of like a bowl shape. It's using x as the variable of integration. So we have our points where these two functions intersect. We have a rectangle, we revolve it around that line x is equal to -1. So as x is the variable of integration, as we could see from this graph, this is a cylindrical shell. So this particular one would be where we use what we were just doing. The volume for this. So for the bounds of integration, which you can actually just see on here on the graph, but to make note of where those came from, we set x squared equal to 2x, subtract over the 2x to get x squared minus 2x is equal to 0. Factor out an x, we got x times x minus 2 is equal to 0. So our two solutions are x is equal to 0 and x is equal to 2, which correspond to the 2 points of intersection on this graph. So we're going to integrate from 0 to 2 pi times. So because we are revolving this around this line, x is equal to -1. Because we're revolving it around that line, let me make note of this. The first term we are going to use for this, we are going to move that 1 over. So we're going to have one factor of x plus 1 by adding that 1 to the left. So we have an x plus 1 here times the function that we have on, since 2x is on the leftmost side of this cross section and then x squared is towards the right, we are going to actually flip our subtraction to be 2x minus x squared dx, since 2x is our leftmost function and x squared is to the right. And we would normally subtract those to find the area between them. And this is being done with respect to x. So we could take out the 2 pi times the integral from 0 to 2 of, we can multiply the x plus 1 and the 2x minus x squared to make x squared plus 2x minus x cubed dx. So integrating this gives us 2 pi times, this will be x cubed over 3 plus x squared minus x to the 4th divided by 4. Evaluate between 0 and 2. If you put in 0 for x, you just get 0 anyway. So putting 2's into all those x's and evaluating, we would get, in terms of pi, 16 pi over 3. Now, with the same problem in mind, let's do part B with y as the variable of integration. This one, we could see now a different cross section. still with our two curves, but notice now, since we want y as the variable of integration, we see the two functions on here, but might as well make note of them. When we have, and let me write this correctly. When we have our first function, y is equal to x squared, if we solve for y, we square root both sides. So x would be equal to the square root of y. And for the other function, y is equal to 2x. We would divide both sides by 2. So we get x is equal to y over 2. And these now would be our two functions that we're using, which is why in this bottom graph here, when we're finding our cross section, which in this case is delta y, the leftmost function is x is equal to 1/2 y, which matches what we have, and the rightmost, x is equal to the square root of y, which again matches our function. So we could see from this graph and rotating that cross section around, x is equal to -1. This is a washer cross section. So to find the volume, we are going to integrate. Now, again, we need to find those integration values. You could see them on the graph here, but from what we saw in that previous slide, right, where the two functions met were at the points of x is equal to 0, and the other one was x is equal to 2. So if we put those into either of the original functions, which one? They both make the same anyway. If we square 0, we get 0 back. So the lowest value we're integrating by is still 0. But now if we take 2 and square it, we get the value of 4. And that will be our upper bound of our integration. So based on that washer cross section, we have pi times, we have the square root of y, but because we're rotating around x is equal to -1, we have to add 1 to this when we square it. Due to that rotation around x is equal to -1, since we have both of these solved for x is equal to, and to get those correct values, we have to add 1. Minus pi times, again, from our second function, this would be 1/2 y. Again, plus 1 for that same reason of rotation around x is equal to -1 dy. So taking out the pi, this is pi times the integral from 0 to 4 of, we would square both of these and combine any like terms with the subtraction. We get 2 times the square root of y minus 1/4 times y squared. And I put a bracket instead of a parenthesis. 1 second. There we go. dy. So integrating that, we get pi times, this would be 4/3 times y to the 3/2 minus 1/12 times y cubed. And we are evaluating this between 0 and 4. Again, as with the last example, you put 0 in, you get 0 back anyway. When you put 4 in, you should get the same answer as we just saw, 16 pi over 3. Again, two different ways to show it based on which variable that you use, and you can compare both methods to see which one is easiest to work with. Kind of depends on the situation. Depending on the variable of integration, as we just saw, that could identify which one is actually easiest. But kind of depends, which may or may not be a good answer for that. One more example, example 3. I want to use the method of cylindrical shells to find the volume generated by rotating the region bounded by the given curves on the y-axis. So y is equal to 3x squared, y is equal to 18x minus 6x squared. So based on the graph that we have on here, this 18x minus 6x squared is a right-hand function. Excuse me, a left-hand function. Left-hand function, and 3x squared is the right-hand function. And you could see that in our graph on here. So based upon that, we could see we can then find, a sample rectangle that falls between those two curves. We can then rotate that around. You could see our cylindrical shell in the bottom graph on here, just to make note of that. To find those points where these two curves intersect, which you could tell from the graph, but without using the graph, we can set these two functions equal to each other. 3x squared is equal to 18x minus 6x squared. Moving the 18x and the negative 6x squared to the left by subtraction and addition, respectively, and then combining like terms, we get 6x squared minus 18x is equal to 0. Factor out a 9x times x minus 2 is equal to 0. We get two solutions. X is equal to 0, or x is equal to 2, which corresponds to this point and this one. So by using x as our with our integration, we get our volume to be the integral from the two numbers we just found, 0 to 2, of, this would be 2 pi times x times, we're going to take 18x minus 6x squared, which again, a leftmost function, minus 3x squared, again, a rightmost function. And this will be with respect to x, so dx. This is 2 pi times the integral from 0 to 2. Combining like terms, we get negative 9x cubed. Negative 9x cubed plus 18x squared dx. So integrating this, we get 2 pi times, this would be negative 9/4 times x to the 4th plus 6x cubed, evaluated between 0 and 2. If you put 0 in, you get 0 back. So using the 2, we get 2 pi times negative 36 plus 48. So combining those, we get 24 pi as our volume. Let me know if you have any questions or concerns. Thank you.